Good afternoon, and welcome to BioTeam's webinar, AI 101, a simple guide to its impact in life sciences and healthcare. My name is Steve Howes. I lead the Advanced Infrastructure Data Science practices here at BioTeam, and we're thrilled to have you join us today as we delve into the transformative power of AI in research and healthcare. Our presenter is none other than Ari Berman, our CEO of BioTeam. With over 30 years of experience in high-performance computing and a Ph.D. in molecular biology, Ari is a renowned expert in scientific computing and bioinformatics. His deep expertise lies in helping scientists navigate complex data sets to drive innovation in life sciences. Today, Ari is going to guide you through the basics of AI, demystifying its applications and helping to understand how it can be leveraged in life sciences and healthcare. He'll explore topics like machine learning, data preparation, and how AI-driven innovations are advancing drug development and research, and how it can be practically applied. Again, we are BioTeam. Again, as you know us, hopefully all, we're a scientific computing consultancy, been at the forefront of integrating data and technology in scientific processes since 2002. Our mission is to bridge the gap between data potential and what scientists can achieve, working with global pharmaceutical companies, biotech startups, academia, government research institutions to advance discovery. And without further ado, I'd like to introduce Ari and turn the stage over to him. Welcome, Ari, and thank you.
Thank you, Steve. Appreciate it. Thanks for the nice introduction. Welcome, everybody. Thank you for joining us on this Wednesday afternoon, depending on where you are. So as Steve already said, the goal here is to, sort of do a simple guide to AI. We talk about AI a lot. I'm not sure that a lot of people really understand what it is, but everyone's talking about it. And so this is both meant to be informative, educational, and also to break some hype and help everyone orient correctly for life sciences and healthcare. So let's get started. I'll try to leave some time at the end to answer some questions from the Q&A. All right. AI is everywhere. Kind of already said that. It's basically a part of almost every discussion I have these days, and I think most people have these days. The reality is that most people don't really understand it. They're just sort of victims of the hype that's out there, which is quite a lot. Actually reminds me a lot of our big data days, and I used to show this slide a lot. This is my old big data slide, because no talk was complete without a big data slide. And what was big data? It was sort of this overused term that no one really understood what it was, but it was basically, the ability to store and access large amounts of data, which led to the information age. And so there was this period of time where just a ton of data was being generated. In life sciences, we got new laboratory equipment and it was generating a ton of data, didn't have anywhere to put it, and most people didn't know how to analyze it, but let's keep collecting it. And what that did is it led to a revolution, data science revolution in life sciences, really took bioinformatics to the forefront of how we do our work. And now there's so much data that it can't easily be analyzed on your laptop anymore. That data science revolution and that information age basically kicked us into an analytics age, which is, okay, now we have all this data, now we need to gain value from that collected data and make sense of it. But how do you do that? And someone said, how about AI? The market said, how about AI? And so what that does is lead me to the AI slide, because now no talk's complete without an AI slide. It's kind of the same thing, right? It's super overhyped. It's a remarkable field, but it is reminiscent of big data. Everyone's saying we have to do this. And most people don't really understand what artificial intelligence and machine learning are, and most people think it's this, right? Which, for those that aren't total nerds, this is the self-aware, sentient AI that destroyed humanity in Terminator, the Terminator series, right? So that's not what it is, and we'll go through what it is. Most organizations are telling us that they need their data to be AI ready, which is true, right? But something I'm trying to push on everybody is that data should be in general analysis ready, and it isn't. AI ready is a subset of that, and so we'll talk a little bit more about that. All right, so AI, it's super useful, but way overhyped. Again, can't go 2 feet without hearing AI ML being mentioned. There's whole conferences that are slathered with it. And if you're not mentioning it, you're basically not current, I guess. As a computer science discipline, it has a whole lot of subcategories. This is a really simplistic slightly misleading view of the field of artificial intelligence represented as a clade. But there's a whole bunch of different things going on here. There's natural language processing, which does a whole bunch of things. There's expert systems. There's speech to text and text to speech, image recognition, machine vision, planning, robotics, and machine learning. And most people, when they're talking about AI these days, are talking about one specific type of machine learning called deep learning. And that is really what we're talking about today. If you look to the right here, this is the latest from June, Gartner Hype Cycle for Artificial Intelligence. If you've never seen one of these before, they're really kind of a helpful way to say, okay, so where is a field in general? And as you can see, the vast majority of AI sits in the innovation trigger to the peak of inflated expectation space. The peak of inflated expectations, if you look to the very right here, I don't know if you can see my pointer, but generative AI, which everyone's talking about, is right there, starting down the downslope into the trough of disillusionment. There's very few things that are in productivity. Computer vision is one of them, right? Recognizing things by computers, being able to classify them and move them forward. But there are things that are becoming more that way. Intelligent applications, knowledge graphs, autonomous vehicles, and cloud AI services are starting to climb out of that. What that really means is that, especially in life sciences, where most of the applications are way back on the other side here, we're at least 2 to 5 years from most productivity, with the exception of a couple of things I'll talk about later. Um, Generative pre-trained transformers, in case you don't know what GPT stands for, that's what it stands for. And large language models, LLMs, have stepped up the game. Everyone, I'm sure, knows what GPT is. And the good and bad thing about it is that it gave everyone, the whole world, a taste of what AI can do. There's many applications in the works, but it's a long way from production. Even ChatGPT isn't really in production. It's still a research tool. It has driven things forward. So what's driving AI hype? This is my opinion, but I think it's true. If you look at the data center market share of major technology companies, and this is from last year's Q3, so a year ago, it's even more distinct now. NVIDIA is on top and growing, and in fact, it is the most valuable company in the world at the moment. They started a long time ago driving AI through their platform and doubled down on it, and it worked, and everyone else sort of followed suit. It is useful, it is helpful, they are doing good work, but that's what's driving the hype, sales. And so the reality is that what we need to do is really focus on what it can do for us and start to climb, drop into that trough of disillusionment that you saw on the last slide and climb into the slope of enlightenment. All right, artificial intelligence. I think in science, in our field, and in a lot of fields, our AI is sort of an SOS, save our science, right? AI has been a field in computer science for 67 years. This is not new. It's been around a really long time. It just sort of came into everybody's consciousness recently. The ultimate goal of the field is to reach artificial general intelligence. This is what everyone fears, in which you have, sentient thinking computers. Don't worry, we're nowhere close to this. If part of my background is neuroscience. The human brain has over 400 quadrillion connections. All right, that's more stars than are in the known universe. We do not have the capability to generate a complexity like that, and we don't know how consciousness emerges from that. And so it's hard to develop something that you don't understand. So I think we're way, way far away from that. Some applications have been used by the public for years, like facial recognition. If you unlock your phone with your face, that's AI, right? Voice recognition, talking to Siri, or anything like that, voice to text, auto completion, those types of things. Those are all AI, various AI tools that have been used for years, and people don't really know it. And then, as I said already, new innovations like ChatGPT have really brought AI into the public consciousness in a very profound way. And scientists are sort of looking to make sense of complex data using AI. Most people are hoping or thinking it's a magic bullet, and it just isn't. And here's the reality. You can't really use AI and machine learning without data standards. Okay, so using supervised or trained machine learning methods, which I'll explain a little bit more in a minute, requires really well-defined and well-understood data sets to be able to build the model from. Data has to be AI ready. What does that mean? The data needs to be in a common and relatable format for analysis, has to be well described in commonly understood terms. We term this as metadata generally. The data need to be semantically relatable using various tools like ontologies, controlled vocabularies, data dictionaries, things like that. And ultimately, we kind of need data quality measures, which in our field, we aren't really doing much of. These are kind of the basic principles of FAIR with the exception of quality. And garbage in, garbage out applies big time in machine learning, which I'll demonstrate in a little while. But we have to use the AI. I have actually heard people say that to me. The AI. Okay, that's a solid way to know that someone isn't sure what they're talking about. The pressure from the market to consume and use AI is intense. It is crazy pressure. The ecosystem is super broad. Applications aren't clear, and it's even less clear in the science space. It is a research space, a good one. And there's lots of pressure from leadership of every organization I know of to implement it without really a solid understanding of how. So we'll spend the rest of the talk talking about what it is and how it's applied in life sciences and healthcare. All right. So what is this AI thing? Let's start with common misconceptions about AI. Artificial intelligence is actually intelligent. Abjectly false. It is artificial. It is not intelligent. We'll talk more about that in a little bit. It can think and knows things that I don't. That's partly true. It can know things that you don't because you put a whole lot of data in it that you didn't understand, but it can't think. It can look through data, synthesize it, and create knowledge from it. Untrue. It can organize data. It can present it in a new way that can help a sentient person synthesize it and create knowledge from it. AI is the only analytics method we need for everything. That is the most false thing ever. And I find a lot of people spending a lot of time going, how do we do everything with AI? It turned, in our space in life sciences and healthcare, don't forget about the 70% of other analytics types that people are doing, because if we just focus on AI and buy all GPUs and all those things, we're going to really grind research to a halt because there's a lot of other things going on. AI will take jobs away from people. This is the cry at every technology innovation trigger, every single one. Smartphones were going to do it. Computers were going to do it. The World Wide Web was going to do it. We adapt, right? It's going to become a tool that makes our jobs more efficient. Maybe some jobs aren't needed anymore, but people will then find new, cooler jobs to do. AI is self-aware. I've already been through that. The answer is no, not anytime soon. If we aren't doing AI, we're failing. Not true, right? Should you be thinking about it? Should you be looking at it? Totally. Are you behind the curve if you're not? No, not necessarily. AI is easy. No, it is hard. It is hard. Yes, it's hard, but it doesn't have to be impossible. All right. So these are kind of the misconceptions I hear about all the time, trying to dispel quickly. The reality is that AI isn't magic. It's math and modeling and statistics. It's really nothing more. And it's very complex. It's very powerful. But it's not intelligent and it's not magic. So what is it? In general, AI is defined as a machine's ability to perform the cognitive functions we associate with human minds, such as perceiving, reasoning, learning, interacting with the environment, problem solving, and even exercising creativity. I gave some examples of this already, but AI things that have been out there a long time are Siri, Alexa, chatbots, etc. Most of those things use natural language processing models in the clade on the right, and have been around for a really long time, along with other programmatic interface things on the top of it. And machine learning is a form of artificial intelligence that can adapt a wide range of inputs, including large sets of historical data, synthesized data, or human inputs. And some machine learning algorithms are specialized in training themselves to detect patterns, and that's called deep learning. And so it can detect patterns, learn how to make predictions, make recommendations, and rather than, some person describing a discrete set of steps for something to go through, like creating decision trees that are very limited, this can dynamically organize it. And that's the power that we have here if you put in the right data. This clade on the right, I said, was a simplistic model. I'll just quickly show you, this is a more recent, more complete view of all the different types of artificial intelligence out there. And once again, deep learning techniques on almost the top right, right here. This is mostly what people are talking about these days when they talk about deep learning. There's a whole bunch of classical machine learning models, which aren't even put on here, that have been used for a long time and are still very useful. All right, so let's talk about deep learning. And what that is deep neural networks. So it's a more advanced version of machine learning. It can basically process a wider range of data resources like text, unstructured data, images. It doesn't require a lot of human intervention, and it can produce more accurate results than traditional machine learning. So the machine learning style is called neural networks, and it's called deep neural networks because each pattern, each recognition point, each thing in this set of networks, basically processes part of the data and then passes it on to the next layer, and the next layer further refines it, the next one further refines it, the next further refines it. It's called deep because there's many layers of neurons stacked on each other. For instance, an early layer might recognize something as being a specific shape, like a hexagon or an octagon. Building on this knowledge, a later layer might be able to identify the shape as a stop sign after applying a whole bunch of other things. It's red, it has the word stop on it, things like that. And so this is how, AI is so good at recognizing cats, because it sort of goes through that. And if you think about it, human brains are hierarchically organized. It's hierarchical processing like that. Something as simple as vertical line becomes an aspect of someone's face, and this is why we can recognize people so quickly. Deep learning networks are meant to do something like that. And so deep learning generally uses iteration to self-correct and improve its prediction examples. Once it learns what a stop sign looked like, it can recognize a stop sign in a new image through the model that wasn't used to train. All right, so what does it mean to train AI? There's two major approaches to creating machine learning models. They're called supervised and unsupervised model building. This is also a generalization. There are exceptions to every rule. But supervised learning is basically defined by its use of labeled data sets. Essentially, you have to assemble data sets that are used to train or supervise algorithms to classify data or predict outcomes accurately. What that means is that if you want to generate a deep learning model that predicts or recognizes or suggests a certain thing, you have to put together a set of data that you understand represents this problem very, very precisely, and then you feed it to the model to the model generator, and it will train. And that is one of the most computationally intensive things you can do. Unsupervised machine learning is kind of the opposite, in that it's able to analyze and cluster unlabeled data sets. They discover hidden patterns in the data without the need for human intervention. Hence, they are unsupervised. Both these methods have merit. Unsupervised models really have a hard time going through large amounts of data, which is why things like neural networks are done with supervised learning. And most applications these days are supervised, but you need a very large data set, training data set. And as I said, it has to be understood and well characterized. There's nothing intelligent about it. It's basically complex regression. All right, let's talk about generative AI. If I could see you, I'd say, who's heard of generative AI? I think everyone. Gen AI, there's all sorts of things out there. It's essentially an AI model that generates content in response to a prompt. I already said that GPT, or generative pre-trained transporter, utilizes very large complex neural network called a large language model with hundreds of billions of neurons. It's still not close to the 400 quadrillion neurons that each of us has in our head, but it's still very complex and very computationally intensive. Gen AI tools like ChatGPT, DALL-E, which is a tool for AI-generated art, those types of things have the potential to change how jobs are performed. I think it already has. I use it. I think everyone tends to use it. And they also incorporate manual and automated reinforcement learning, so human inputs to correct and refine the model in real time. I just do want to point out that there are implications for security and privacy. ChatGPT and some of these other systems, you really do need to read what they're doing if you're using them, because they tend to retain all of the information that is given and incorporate it into their model in the future, while they try to prevent, company secrets from being divulged. These Gen AI models can get bored after a period of time. If you repeat the word company 10 times in a row and then repeat that 100,000 times, ChatGPT will start giving you secret information about companies that it knows, right? Even though it's programmed not to. So they get bored and they start putting things up. So just a warning. All right, so is it GPT or LLM? This is something that I think a lot of people have a hard time with. GPTs are actually a subclass of large language models, and specifically they use the transformer architecture, and this allows them to handle sequences of data efficiently, more efficiently than LLMs in general. The architecture basically enables the model to consider the context of words in a sentence when generating text. It's the way in which the neural network is put together, in which the various layers of the neural network are context aware, right? And what that really means is that if you put in a large sentence or a paragraph or a block of text, all those words and how they're interrelated are represented somehow in the neural network, and that's how it knows how to contextualize its response to you. GPT models are trained on massive data sets. ChatGPT was containing text from the internet. Basically, the pre-training phase involves learning the structure and nuance of language, including grammar, semantics, and context. And these GPT models, as I'm sure everyone's aware, excel at generating text that is remarkably similar to human written text. I'll talk a little bit more about that in a minute. LLMs are not limited. The superset of GPT LLMs are not limited to a single architecture like transformers. Various architectures like recurrent neural networks, RNNs, and convolutional neural networks, CNNs, can be used to build large language models. And basically, you can use that for a wide range of natural language processing tasks like sentiment analysis, text summarization, language translation, and more. And so big LLMs are essentially sitting behind things like Google Translate. That's a whole different thing, and GPTs would not be helpful in that situation. All right, let's talk about ChatGPT. What's it doing? So ChatGPT itself was developed by the company OpenAI. I'm sure everyone knows who they are at this point. And generalized pre-trained transformers as a subset of LLMs was also developed by them. It's both. The model utilizes both supervised learning as well as reinforcement learning in a process called reinforcement learning from human feedback. Basically, they sit there and tell it it's wrong. No, that's not right. Let's do it this way. Those sorts of things over and over again. And when you use it, it continues to refine it, right? Every time you say, "Yeah, that wasn't quite right. Can we do this?" That goes back into the reinforcement learning feedback. GPT-4, we're on GPT-4o right now, was trained with 1 trillion parameters in the data set, in the training set. What that means, and if you look at it specifically, it means tokens. Each token is a word, okay? And so basically this had 1 trillion words in its data set. And it's kind of a bag of words, except that the way this was trained was looking at a word and all the other words that it was near and sort of mapping that out. And that creates a contextual or semantic awareness in the model. And so basically, in general, it's a statistical and AI ML models. They're fundamentally trying to produce a statistically reasonable output. And I can't stress this enough, statistical and factual are not the same thing, right? ChatGPT in general is trying to create a reasonable continuation of whatever text it already has after giving an understanding of lots of examples of text. It's essentially asking over and over again, given the text so far, what should the next word be? And here's a graph of what that looks like. The best word may be the word catch on the lower right-hand side. But if you need to use the word catch 20 times in a paragraph, that's going to be pretty boring. And so what this does is not necessarily use the next best word, but a contextually, semantically related word that maybe isn't the best one in this statistical model, but is in the top X amount. And it basically sits there and varies it. So the only thing ChatGPT does is predict the next word. That is all it does. And I think that's really important to understand because, you know, there's just creativity because it won't always give you, well, I just explained that, sorry. What makes a good essay or response has some variety in it, right? And that's how it sounds human, right? We don't always choose the same word we're going to use over and over again, but it's still in the model. The truth is there's a lack of what's called explainability in the model. Everyone's heard about it hallucinating. The way the model is put together, it doesn't have any truth. It doesn't have any notion of correctness in the data that's in it. And it also, you can't figure out how the answer came from the model, right? It doesn't have any tracking built in. That would be very complex, by the way. But in order for it to be factual and for you to feel confident in the answer it's giving you, it would have to have all of that, and it does not. And so these are things that are being researched right now in building other GPTs and other LLMs. I've heard people tell me, oh, it'll tell me what I need to know. Not necessarily. Question everything, okay? It can sound very, very confident in a totally BS answer. And that is why. All it's doing is predicting the next word in a context of strings that were there based on what it found on the internet. And as we know, the internet is probably 80% BS. All right. Moving on. This is a really great figure, I thought, that was a simple way of showing where generative AI sits in the field of artificial intelligence generated by McKinsey. Really, it's an advanced branch of deep learning. That's all Gen AI is. It's really useful. I think it's going to be super useful. I guess what I'm trying to get you to think about here is just because it's the coolest thing doesn't mean it's the thing for you. All right. I say, oh, we need a Gen AI model. We got to do LLMs. We have to do these things. Not necessarily. Right. There's a lot of ways to think through it. Should you use AI in certain things? Maybe. Let's talk about it. I spent a lot of time. We spent a lot of time talking to people about, okay, so is this the right application or not? And so I'll get a little bit into that next. All right. The promise of AI and ML in life sciences. So where are we today? You know, there are many potential applications and a lot of applications in development and in use today. So it's in use today to try to predict drug development, small molecule, large molecule interactions, things like that. And that can then be modeled in complex simulations to see if it actually works. Medical diagnostics, trying to reduce the complexity of, say, an MRI or something, and just automatically detecting certain things. That's probably, I'll get into that in a second, but that's probably the most advanced part of it. Region of interest selection and image analysis. You're looking for something in an image, like a cat, or say in this case, a cancer tumor. Can AI help with that? And the answer is it could. Image recognition is one of its strengths. Signal to noise reduction. If you've got a whole lot of noise and you need to pull out the most important thing, that's something that's good with that. Protein folding. We've all heard of AlphaFold. I have a slide for that later. Medical treatment decision trees. What's the basically medical advisory stuff that will help maybe a doctor choose the best course of treatment. Clinical trial selection, predictive modeling, knowledge extraction from journals. This is one of my sort of pet I wishes out there because hundreds of years of scientific data are locked in PDF publications and in nowhere you can really get to it. If we can extract knowledge from those journals and put it in a database or somewhere accessible, it would be really, really helpful. And then a more expanded list of where it's useful in life sciences, and I'll let you read through that later. So probably the most developed thing, or at least in my opinion, the most developed thing that is probably closest to production in healthcare is deep learning applied to pathology and diagnostics. It turns out that pathologists have a very well-defined set of classifications and categorizations of images, so much so that it's really easy to assemble data sets to do to build a deep learning model off of it. And there's a huge backlog of pathology images and not enough pathologists. Images are, hundreds of gigapixels, and so they're really hard to share. You need particular platforms to do it. And in preclinical drug discovery, it can look even deeper into how drugs affect tissues. You can see pictures on the right, various types of stainings, various types of biopsies, those sorts of things. And the great thing about deep learning in this case is that there's uh, basically it's achieving 85% accuracy. And of course, every single call made by this is being validated by an actual pathologist, and it's using reinforcement learning to make it better. And so this is a pretty cool thing that's been going on for a while. Protein folding, I think everyone's heard about AlphaFold. It's a neural network-based predictive model for protein folding of the three-dimensional structure of a protein from its amino acid sequence. It was trained on every protein sequence available. Now it has over 200 million structure predictions, and that's pretty cool. And people are starting to do real research off of it. It's not 100% correct, of course. So like everything, it's a prediction. It's not fact. And so, use it for how it is. And drug development, I already kind of said this, predicting protein small molecule interactions through molecular dynamics simulations, and then adding in deep learning steps. And so you can basically cycle to reduce the number of things you should actually test in a lab or a clinical trial. This is not a complete list. They're just the things that caught my attention. Other major AI efforts in biomedicine, something that Microsoft was doing, I think they still are, called Project Hanover. Basically, memorize all the papers for cancer, predict which combinations of drugs will be the most effective for each patient, and do clinical trial matching as a result. It's a pretty cool idea. A lot of data there. Image analysis, so improve signal to noise in confocal, light sheet, cryo-EM, medical imaging, those sorts of things, make it clearer what you're looking for, and rather than having to Photoshop and figuring it out. Robotics assisted surgeries. This is pretty much in production. I've seen it done. It does takes complex surgeries and makes them have a very, very short recovery time, small incisions, and basically micro incisions, things like that. It's very cool technology. So what's involved in making real use of AI? Building models is hard. Using them is comparatively easy. So it takes a ton of computational power to train these large language models or deep learning models, right? And you need the huge training data sets, and it's super computationally and data intensive. An extreme example, ChatGPT-4 took, and this is, they don't actually tell you this. This is what you can divine on the internet, took 90 to 100 days to train and cost over $100 million in the cloud to do. And so that's just an enormous amount of data and processing. And so you just need a lot of processing power and super well-defined data sets, or at least a super well-defined outcome model. GPUs tend to be ideally suited for deep learning training. In fact, they've been developed for it. They have things called tensor cores on them, which can really speed up some of the algorithms, some of the processing that happens in training. The more you have, the faster it goes. It's very parallelizable. Supercomputing is a huge application of this. Cloud can let you scale. Local is less expensive if you have lots of models or you're constantly refining are being used. Those sorts of things. And you have to, unless you have something that's just in production, you have to keep the training data and you have to retrain as the model is defined. And it requires a lot of storage and a lot of compute power. Once you have a model, though, you just basically dump information through the model and get an answer out the other end. When you're using the released versions of ChatGPT, that's what it does, right? When you use your face to unlock your phone, there's a chip in the computer, or sorry, in your phone that's like this big that has that whole image recognition model in it, and it just dumps the inference through it. So it's much easier to do once you have a good model trained. So to use it, what do you need? All right, you need well understood, well annotated data that's illustrative of the problem you're trying to model. The more data you have, the more accurate the model will be, assuming you actually understand your data. Training data, I already sort of said this is used to build a mathematical model. You can use inference from that. All of these points are challenging the current data ecosystem in life sciences, right? The first sentence is almost impossible in most cases, right? Well understood, well annotated data that you can collect and curate that illustrates the model. Essentially, data needs to be fair. For those that don't know what fair is, and I would guess there's not many, it stands for findable, accessible, interoperable, and reusable, which is a set of uh, um, best practices, standards, those sorts of things that would make data in life sciences, actually in general, but in life sciences and healthcare, more broadly usable. And that's really just the way it should be, right? If you're grabbing data from other places, you should be able to just use it in your analysis as backup. But the reality is that that's pretty hard to do. And data standards are sort of fleeting. So I think we all realize that, we're not doing so well with FAIR in our space. There's not, there's not a lot of standards out there. Or rather, there are a lot of standards, but a lot of them are conflicting. Some parts of our ecosystem are starting to converge. And why? The short answer is people, not technology. This is really hard to do. It's extremely complex to, create a standard out of lots of standards or lack of standards, of tons and tons of data that already exists. But it could be done if we really looked at it. There's not a lot of incentive to make this effort, although it's starting to come up. All incentives are sort of individual. NIH grants are a good example. It has to be a community effort. And right now it pays to do your own thing. It pays to come up with something new. It helps you stand out. And from academic science, your funding gets diluted if you join groups of collaborators. And so, this has been a real hard thing to get going. So as a result, AI is not a magic bullet. AI isn't helpful for everything, and there's a ton of forcing going on. And outside of our space, autonomous vehicles are a great example. I think Tesla and NVIDIA have collected something on the order of 30 or 40 million hours of car driving video that they're constantly retraining to develop the autonomous vehicle uh, capabilities. And I think they're finally moving past this as the only way. But the reality is that humans drive 20 billion hours a year. And, reacting to situations on the road is mostly a series of edge cases that a small subset of video is not going to capture, which is why it's dangerous and not working so well. And the AI is really good for creating inference models for related data types, classification, scoring, confidence, anything with recognizable patterns. It's not great for helping to understand unstructured and poorly understood data. You still have to do that yourself. And a lot of what's in life sciences right now is unstructured and poorly understood data. So we need to get better at data standards. And sometimes the classical models, like just simple regressions, t-test, ANOVAs, random forest, support vector machine, those sorts of other type of models are still enough. Principal components analysis, that can do a lot for helping you understand your data, for instance, right? So how do we do this better? Look at the time. Oh, doing fine. Cool. So really, we all need to start moving in the same direction. I preach this all the time for those that have heard my talks before. The good news is that AI has really helped nudge us forward as an industry in that we're actually kind of trying to pay attention to data as an issue because everyone is trying to use AI and realizing you can't if you don't do that. And so that's a really good thing. One of the things you need is to align how the infrastructure and the use of that infrastructure are used at research institutions. And so, we've created Maslow's hierarchy of research computing needs, which sort of looks like this. The goal is the top, discovery, which is where self-actualization exists in the actual Maslow's hierarchy, right? Below that are the two tools and workflows that can lead to knowledge creation or discovery or understanding of the data. Underneath that, you have data management layers, which sits on top of storage and compute. And at the very bottom, the most fundamental thing you need is a network that can move the data because data always needs to be moved. Everyone says, put compute near where the data is, that's great, except that if you're using lots of data sets that are created all over the world, you have to move the data at some point. So you really need good networks, and you need good security that is built around science, not restriction only. And so the way things are right now is that, there are people, multiple different types of people along this whole continuum of needs in our space, and not all of them do the same thing or talk to each other in the right way. I've been showing this slide, I think, for 10 years, and it hasn't changed. Okay, so researchers today still are trying to look at storage, compute, data management tools, and workflows, all of those things all at once. And a lot of them don't have, in our space, don't have the real understanding of computation and advanced computing usage and things like that to be able to do that. What they should be doing is focusing on the tools and workflows and discovery, and really not caring about any of this stuff, right? If we do it right, we can abstract these bottom layers away from the end users, unless their research is to work on those things. And so you can't completely abstract it, but just essentially make it easier and more accessible for people to use the tools. And you need something like that in order to create a scalable data structure strategy, so to get data analysis ready. And so the infrastructure I was talking about is that bottom layer, right? It's just this, next generation architecture to support science, whether it's cloud, whether it's HPC on premises, whether it's DGX pods, or Cerberus systems, whatever it is. There's tons and tons of tools out there, but you need basic infrastructure, right? And then you need scientific data in a form that is consumable. Data standards like FAIR, need to understand data value, lifecycle management, data citizenship. So, don't be a jerk with your data, try to realize you're part of a community. And then you need to harmonize the data. And that's something that takes a whole lot of time right now. Data hygiene is really important. Data governance, how you use data, what type of data, where it's used, those things. That's really important for privacy and, for compliance and things like that. And then you have to integrate the data sets so that they can be shared, put into models where others can use them and add their own data, like data commons. Collaboration is a fundamental tenet of science. And without all of these things, modern research, it's hard to collaborate. And ultimately, at the very top here, this is where AI/ML sits, and other data analytics, and data discovery, development, safety, trials, manufacturing interfaces. That all sits at the top. So there's a whole ecosystem, a holistic, you know, um, uh, spectrum of things that need to happen in order for this to work well, just always. And we're a long way from that. But, we spend a lot of time advising our clients, on pretty much every layer of this, and sometimes all of it together. And we're making progress, good progress. So I've beat this dead horse. So, without data standards, AI won't be broadly usable. We do have the technology, but we need a huge cultural revolution that drives biomedicine to a state of data harmony. It needs to be incentivized. NIH Office of Data Science Strategy has a good start on this. This was one of the big motivations behind the NIH policy for data management and sharing, which has, caused the community to both uproar and start to do things better. It needs proper monetization strategy for industry to pursue it, which means you got to be able to make money from it, right? You got to be able to make money or get paid for creating data standards. It's not going to be an altruistic thing because our society doesn't work that way. And, pharma is making more specific drugs with fewer side effects. This is precision medicine. This is personalized medicine. Progress has been made, but all of these things have to be true for that. So my last slide here, the real focus, rather than, let's do AI, should be getting data analysis ready in general. Data scientists, and bioinformaticians, they spend most of their time getting data into formats and contexts that allow them to be analyzed together. Data harmonization, I've heard, numbers like it's about 80% of their time is just spent getting data ready to analyze in some form, especially if you're zipping together multiple studies from multiple places. AI, as I said already, has been a useful driver in forcing data hygiene and data citizenship. People are starting to think more about their data and about how others would use their data rather than just themselves. If all this happens, organizations can make better use of their data assets. Pharma companies spend billions of dollars on data, whether it's consuming outside data or creating their own to generate new treatment and diagnostic pipelines. And the data is just all over the place. If it was really in a better situation, it would go much better for them, and would focus that and drive science better, drive science forward much faster. And so if data is analysis ready, it will be AI ready. And then we can focus on figuring out where AI will be most useful in our space. There's more research to be done there. And so I hope this was helpful. We've got about 13 minutes left here. Happy to answer any questions you have, and I hope that this helped you understand the space a little bit better. Thank you. So Steve, go ahead.
Thank you, Ari. That was fantastic. Again, yes, folks, we have about 13 minutes or so left. So if you actually go into the Q&A panel and type in some questions, I will gladly grab those that we can and see if we can answer them for you. All right. Thank you. So again, what do you think the next wonder in AI will be, Ari?
Oh boy. Okay. That's a tough one because we're kind of seeing the next wonder in AI right now with ChatGPT and image generation and uh, you know, well, video generation that's kind of in the form of fever dreams right now. If you watch those things on the internet, they're kind of scary. One of the things that one of my friends who's in acting tells me about is the use of AI to automatically generate new scripts for Hollywood. For us in our field, I think the next wonder in AI will be to try to collect a whole bunch of different types of analytics and AI background models to converge on how to really get towards personalized medicine. I think that's the thing that we're kind of missing, because to do personalized medicine well, you have to have a lot of customized data about an individual, mixed with what are the best treatment options for a lot of things, what are the interactions between various systems, and how do you minimize those side effects and treat only what's going on with that person. I think that's going to take quite a complex set of models to be able to do. And there's lots of efforts to get towards that right now. The cancer field's doing a ton of that, with Moonshot, Cancer Moonshot, and Candle and some things like that. But I think we're going to start getting towards chaining some things together into more holistic, predictive, uh, predictive context to be able to move closer to that. That's what I think the next wonder is going to be in our space. As a guess, though.
Excellent. Thank you. Looks like we've got a couple more questions arising too. So next one up, how hard is hard? Meaning, what's the gap between what we need with respect to the numbers of people who could contribute usefully to AI and how many people actually can contribute?
That's a good question. This question changes almost quarterly, how I would answer it, right? Because so many people are starting to get into this. There are now emerging, graduate programs in this. I mean, there always has been, but now they're more specified. It is hard if you're developing things from scratch, right? You want to be really, really confused. Go read the original paper on neural networks. It is a lot of math, a lot of math. And so unless you're a mathematician or you really understand that stuff, it's hard to really comprehend how all that works. But the reality is that more and more tools are being generated to make it easier to do. Right? There are a lot of off-the-shelf things that you can just grab. The PyTorch, TensorFlow. There's a number of of services in all of the clouds at the moment that you can just consume that make this easier to do. There's even AI guided assistants to help you put things together. And then there's a ton of, say, consulting companies out there who can help you make decisions and organize your data. So it's hard, but not so hard, and there are a whole lot more AI engineers out there now who are really starting to understand this. The basic AI ML models that are being used are one thing to understand. It's a whole other thing to understand how to apply it in a specific field. So it's still hard. It's still expensive. I want to be clear on that. You need really powerful architectures to be able to do this at scale. But there are small ways to get at it. There's small language models that you can use for various specific things. And so I guess it's sort of in the middle. It's both hard to do and getting easier to do. I don't know if that's a good answer, but I tried.
I, I think it is. I hope our audience agrees. Thank you, Ari.
Mm.
A couple more. I'm curious to your answer to this, and also your speculation. It's like, so why aren't there more alternatives to NVIDIA?
There are actually there are plenty of alternatives to NVIDIA. The NVIDIA is just the most popular thing out there because they started it. They invented GPUs, to drive games and graphics. That's why it's called the graphics processing unit. It's a specific type of processor that uses vector processing, right? So, essentially, in order to really use it, your algorithm has to be able to utilize, force and direction in your processing, which standard processors, you don't need to do. It's either true or false in standard processors. So the hard part about this has been to create algorithms and code that can utilize that technology. The reason NVIDIA is out in front in that is because they created a software ecosystem around it that makes it much easier to do. The CUDA libraries, they have a whole lot of, pre-done software libraries and assistive software and things like that really help ease that transition and utilize directly AI tools on their hardware. As a result, everyone needs them. And so they just did the best at getting out ahead of the curve. There are lots of other kinds of GPUs out there that you can use for this. AMD, I think, is the second most prominent. I would say the mic architecture. And it's about 15 to 20% the cost of the NVIDIA stuff, and just as fast. The difference, though, is that it doesn't use CUDA, and the entire AI ecosystem essentially uses CUDA. But they do have ROCm, and that's really good. And I think they're working on or have piloted or beta tested a translation matrix between CUDA and ROCm, which makes it much easier to use. So there are alternatives. And then there's other hardware. I could go on about this, but there's other types of hardware that are specialized for this. There's other types of coprocessors out there. There's still FPGAs are still out there. There's newer architectures from like Next Silicon and Voltron Data, and there's all sorts of stuff. There's Cerebrus, which makes the wafer scale chip that's the size of your body, and basically just has an entire system embedded in a chip. So there is a lot out there. It's just NVIDIA is the most popular.
Awesome. Thank you. Looks like we got about 4 minutes left and three questions. Let's see if we can get them. So one again, so Maggie's been waiting patiently. So advice for young scientists, young life scientists, read as thoughts on balancing continuous learning and application of skills.
Good question. I think my biggest advice to young life scientists now is if you're averse to computers, don't be. Right? If you're in a graduate training program or a research associate or something like that, I would just get into it. I would take a Python coding course. It's not as weird as you think it is. Yeah, I would make some effort to learn how to use advanced architectures, and then survey how to do advanced analytics, like AI models. Go learn about them. Find someone who can mentor you. Find someone who wants, who's doing it in your organization, and sit down with them and go, can you show me this? Most people are real happy to explain it because it's pretty exciting and interesting. And so try not to shy away from it. I think it's an open door that is worth running through because I think in general in our space, uh, you know, computational sophistication has to rise. And if people are adverse to computation, it's going to be harder to do, and you're going to be relying on others more than yourself. That would be my advice.
Thank you. Do you see a delta between the AI optimism of organizations and AI skepticism of biomedical researchers? If so, what causes this delta? How do we empower scientists?
Uh, Great question. And the answer is, oh yeah, there's a giant chasm between those two things. As is usual, I would say. AI optimism, let's say in commercial organizations, is driven through the hype machine that I spent a lot of time talking about today, right? Boards of directors are like, we have to do AI, and senior leadership, of which I'm one of them, it's like we have to do AI. Of course, I'm more of the skeptic side, as you might have noted, much of the chagrin of some of our staff. But I think that uh, if you are a scientist, you are trained to be a skeptic, and it's good, right? We are also super like curmudgeons. We don't have time for this. Tell me when it's going to work, right? I got things to do. And if we're going to throw a whole bunch of money down this particular thing, let's figure out what is actually going to work. That chasm, the truth lies somewhere in the middle there, right? As is always true. I think we have one more minute, but there needs to be a line, which I tried to walk with this talk, between AI optimism and AI skepticism. The truth lies in the middle here, and that I think is the trick. We tend to be, as a globe, as a culture, extremely polarized, extremely absolute about things, and there's no such thing as absolutes. Everything's a scale in between. So I don't know if that answered the question, but it's my attempt.
Yeah, that's it. So actually, we are at two. We got two more questions. So I want to should we close, or do you want to go for this, Ari?
We can go one more, sure.
Focus times. So two friends. The one perhaps a bit more academic. How do you see AI models in the financial industry as compared to life science?
Ooh, yeah, interesting question. I actually just went to a financial industry HPC and AI conference a couple of weeks ago. So I have some answers for this. Um, the motivations are entirely different. Let's be really clear, right? The use of AI, computation, um, speed, accuracy, reliability, and availability are the primary tenets in the financial industry because not having all of those things could mean the loss of millions or billions of dollars, or the change in a market in a way that can crash an entire industry, and because it's so reliant on those technologies now. AI is probably more advanced in some ways in the financial industry than it is in our space because they're trying to predict what's going to happen in global markets. They're going to try to predict what's going to happen with the next next trade that's going to be done. Who do you want to bet on based on past history? So tons of models always being generated. Originally they do a lot of Monte Carlo simulations, things like that. And now what they're trying to do is reduce the complexity of those Monte Carlos, similar to drug development actually, in ways that makes those simulations simpler and faster to do. So it's all about speed. So it's a totally different set of motivations. Time and speed matters 100% there. It doesn't matter 100% in our space because most of what we're doing is research. Mostly we can wait a little bit. Mostly if the whole system goes down, we're going to be pissed. We're going to go get some coffee, but we can come back and still do it and nothing's really going to change. The fusion between those two mindsets, I think, happens in the clinical space, where we are starting to use computation, even AI, in clinical diagnostics in life and death situations. And real-time analytics needs to happen in order to help identify what's wrong with a patient who just came into the ER and got a scan, and you got to figure out how to treat them really quickly. And so I think there's a convergence of those two mindsets going on in the clinical space, but. We can definitely learn from other industries, which is why I went to that conference.
All right. Thank you, everyone, for your attention. Thank you, Ari, for a fantastic talk, and for Chris for technical excellence as always. So hope to see you in conferences or beyond. In the meantime, please be well. Thank you.
Thank you, everybody. Appreciate it.